Spooky action at a distance is something that Einstein and Schrödinger both worried about. Less worry from the quantum mystics community. Nonetheless, this talk will look at the underlying theoretical and experimental situation relating to that. And our speaker will examine the notion of quantum entanglement, which trips off the tongue in everyday conversation all the time, and ask whether it's spooky, as it's sometimes cracked up to be. Alan Stair is a member of the philosophy department at the University of Maryland, where he is the associate chair. His research centers on issues in the foundations of quantum mechanics.
Thank you very much. I'm delighted to be here. Thank you for the invitation. And what I want to do is mainly give a talk that goes over a lot of kind of historical background and so on that will help you see where this issue comes from and a little bit about what physicists might say. Most of that is going to not really touch on the sort of larger issues that people interested in skepticism might have in mind, but they will definitely come up once we've set the stage at the end, and we can certainly talk about it in the question period. So, our agenda is going to be this. What I'm going to do is I'm going to sketch perhaps the most famous argument bearing on this whole subject in physics, the so-called Einstein-Podolsky-Rosen argument. And this is an argument that Einstein had a part in developing, which was intended to show that, as Einstein and others saw, that quantum mechanics was incomplete. So I'll explain what that means. And then we're going to identify a presupposition that this argument makes. And we're going to set forth what in the physics community, in the philosophy of physics community, is a very well-known reply due to the physicist John Bell. And then we will say some things about entanglement, locality, and spooky action to distance, all these wonderful phrases. So, what I want to do is I want to go back to 1935 when Einstein and Boris Podolsky and Nathan Rosen published this famous paper, Can Quantum Mechanics Be Considered Complete? And I'm just going to sketch briefly what they had to say because it sets the stage for the kind of worries and problems that we're interested in here. But the first point is this. The way that people thought about quantum mechanics, and in many ways many people still do, is this. If quantum orthodoxy is right, if the usual way of thinking about quantum mechanics is right, then if you've got a quantum system, think whatever you like, an electron, an atom, it doesn't really matter. We normally think of things as having a certain position, they're located somewhere, and they're going at a certain speed, and depending on their mass, that means they have a certain momentum. So that's how we think of ordinary things around us. They are somewhere, and they're moving in a certain way. But if the usual way of thinking about quantum mechanics is right, this sidebar to Heisenberg's uncertainty relations that we won't actually discuss directly here, then, well, especially at the quantum level, that can't be right. It can't be right, the orthodox view said, that something is both well located and moving at a different speed, a definite speed, pardon me, at the same time. We can say more about that later if we like, but that's a very standard way of thinking about things. And what EPR say is they say, well, this orthodoxy can't be right. And they argue that it can't be right by offering a certain kind of common sense principle. And I'm just going to kind of sum up their principle here. So suppose there's this quantum system over there, and I'm doing some measurements here on another quantum system. And suppose that by doing my measurements here, I can make all kinds of predictions about that system over there. Maybe I can predict what would happen if you measured its position. Maybe I can predict what would happen if you measured its momentum. Now what EPR say is that if I can make those predictions, and I can do it without disturbing that system, without interfering with it or interacting with it, then there's got to be what they call an element of reality that is responsible for the fact that I can predict what would happen if you measure the position or if you measure the momentum. Put briefly, there must be a position, or there must be a momentum over there. It's not created by what I do, but it's already there. Okay? Now, what they then go on to do is consider a special sort of a state of two quantum systems. We won't get into the technical details. All we need to do is understand how the system works. So we've got these two separated systems. We'll just label them 1 and 2. And they're in this special quantum state. When I say special, it's not exotic. It's just a particular kind of state. And the way it works is this. If I have one of these systems in my possession, and I measure where it is, then I can predict perfectly what someone over there would find if they wanted to measure exactly where that system was. So I find the position here, I can predict the position over there. But on the other hand, if I wanted to measure the momentum of my system, let's just think for the moment about how fast it's going, well, I could do that, and likewise, I could predict the momentum of that system over there. Now, it turns out that I can't do both of these things. I can't measure both the position and the momentum of the system at the same time. They interfere with one another. But I can pick which one, and whichever one I pick, I will be able to predict the corresponding experimental result over there. So what EPR would say is, look, if I want to predict that system's position, I can do it without interfering with it. On the other hand, if I want to predict its momentum, I can do that too. It must really have a position. It must really have a momentum. This seems like a very common, sensible way to think. In spite of the fact that no quantum state, the state in quantum mechanics is what you used for making all of your detailed descriptions of the system, no quantum state will tell you both of those things at once. And so Einstein, Podolsky, and Rosen say quantum mechanics must be incomplete. There must be some information missing here. Okay, now, what I'm going to do is I'm going to describe the version of this argument that tends to be thought about these days because the experiments are a lot easier to do. So we're going to introduce a term here. The term is spin, and we don't need to worry about the physics of it in any way except this. Things like electrons can be measured for their spin. It's measured in whatever direction you pick. I can measure spin in this direction, I can measure spin in this direction, in that direction, whatever you like. And if I measure the electron spin in some direction, I'll always find that it's either +1 or -1. Sometimes put up or down. And that's just a fact about the quantum world, okay? You don't need to worry about why and where that comes from. It's just something about electrons. Now I can pick whatever direction I like. So I've got this directional property spin. And I can pick a direction and I can measure the spin in that direction. But I can't measure in two directions at the same time. Just in the same way that I can't measure position and momentum at the same time, I can't measure spin in this direction and this direction at the same time, for example. Okay, so now what? Well, we can set up this special state. This is called the Singlet State. That's just its name. Don't worry about why. And this is a special state of a pair of electrons. So suppose that our two electrons, 1 and 2, are in this special state called the Singlet State. And no matter what direction I pick to measure, let's call it D, if I measure the spin in direction D, and someone over there measures the spin in the same direction on their particle, we'll always get opposite results. If I find +1, they'll find -1. If I find -1, they'll find +1. And it doesn't matter what direction we pick, as long as the directions are parallel. Okay? That's just a fact about the quantum world. And that's kind of interesting. You think, gee, I mean, there's obviously some sort of really interesting correlation between these two things. How does that work? So, you know, this is just a coiny little picture, but the idea is that I've got these meters set to measure in the same direction, and they show up with opposite results. Okay? Different direction, if it was the same direction in both cases, I measure the two, I always get opposite results. So that's just a little image, if you like, of what's going on here. Now there is a technical note that you don't need to worry about, but it's just this. I have to do this pair by pair, because after the first measurement, the correlation is broken. This correlation is very fragile. It lasts for one measurement and then it's broken. But I can take a whole bunch of pairs, all in the singlet state, you know, hundreds of them, and measure and measure and measure and measure and do it in all kinds of different directions and notice the sorts of correlations I get. And that's exactly what they do. All right? So, here's the version of EPR's argument with spin. If you've got two electrons in this singlet state, then no matter how far apart they are, when I measure the spin in any direction on one of them, that allows me to predict the spin in the same direction on the other. It doesn't matter what direction I pick. EPR would therefore conclude I'm not interfering with that particle over there. I'm not interacting with it. So apparently the spin in that direction for that particle must already be real, must already be definite, and it's just like me sending a letter to you or to you, and when you look at your letter, you're going to know what it says. That was the kind of model they had in mind for what's going on here. No mystery at all. But the same goes not just for the d spin, it goes for the spin in any other direction. Just call it d prime. However, just as with the position momentum case, quantum mechanics never tells you the d spin and the d prime spin at the same time. So once again, EPR would say, there's something missing from quantum mechanics. This was their issue. They took it for granted that there's no spooky action at a distance. They took it for granted that what happens to this system doesn't do anything to the distant one. They were concerned with a question of a different sort. If that's what things are like, and if you have the correlations that quantum mechanics says you have, can the theory really be complete? Can the so-called quantum state really be telling you everything there is to know about the quantum system? And they concluded the answer is no. But what their argument leads to is what I'm going to call the definiteness hypothesis. And the definiteness hypothesis would say this. If we've got two electrons in the singlet state, then no matter what direction we pick, both of the electrons have definite spins, opposite spins in fact, in that direction, no matter what direction. And if we made a measurement, we find them. So it might be that in this direction mine is +1 and that one is -1. It might be that in this direction mine is -1 and that one's +1, and so on. But if the definiteness hypothesis is right, that's how the quantum world is, and EPR thought their argument establishes the definiteness hypothesis. So the question is, were they right? In particular, is the definiteness hypothesis testable? Does it have consequences that you could take into the lab and look for it? Because the problem is that the EPR debate and the debate that they had with the famous physicist Bohr, who was the orthodox representative of quantum mechanics, the debate there is too philosophical. It doesn't directly get any grip in experiment. So we need to go further, and in fact it turns out, as the physicist John Bell explored in detail in the 60s, this so-called singlet state leads to testable predictions for this definiteness hypothesis, for the idea that the spin is always fixed no matter what direction. And so what we're going to do is we're going to come at these predictions by a little simplifying detour. I'm going to start with something that isn't actually quantum mechanical, but will help you get the idea of where the problem might come from, and then we'll try to make it a little bit more true quantum mechanics. But the ideas here came from the physicist John Bell, who died in 1990, as the slide said, and who really transformed the foundations of physics by allowing us to raise in very precise ways questions that were hitherto only philosophical, if you will. So the eventual key to the test is making non-parallel measurements, but before we say anything about that, what we're going to do is just sort of talk through a kind of imaginary example. So this is partly imaginary, but here's the idea. So far, everything, this should say 1 and 2, by the way. If 1 and 2 are in the singlet state, then we know that parallel spin measurements are going to give you opposite results. But if we measure the spin in directions that aren't parallel, well, then it turns out that there still are correlations. They're imperfect correlations, but they're correlations. It might be that there's an 80% chance that the two measurements will agree. And it turns out that when you look at those imperfect correlations, that's where you get problems with the definiteness hypothesis. But first, we're going to consider what I call supercorrelations. It's just a word I made up to briefly describe this little example. The example doesn't come from me, but it's a nice one to get a grip on things here. So we've got, in the foundations literature, people like to talk about Alice and Bob. Whenever you've got these experiments, one person doing a measurement here, another person doing a measurement here, it's Alice doing one measurement and Bob doing the other. And in fact, at the Perimeter Institute for Quantum Mechanics, for Foundations of Physics up at Waterloo, Ontario, they have these conference rooms. And one of the conference rooms is the Alice room, and the other one is the Bob room. And as it turns out, I've given talks in both of those rooms. So take that as a small bragging right. So what's going to happen then is we've got this imaginary supercorrelated state. Alice is going to measure spin in some direction that we'll call A0, or in a direction A1. Doesn't matter what these directions are, we'll just assume that they've been fixed in some way. And Bob is going to measure spin in direction B0 or B1. He gets to pick. Now, is A0 the same direction as B0? No, it doesn't have to be. Okay. But we're just tagging these directions. We're just giving them names. A0 and B0, A1 and B1. So here's how the supercorrelated state works. And you can kind of keep this in your head. That's what I like about this example. Okay, first bit. If Alice measures A0 and Bob measures B0, their results will definitely agree. They'll either both get +1 or both get -1. That's easy to remember. If Alice measures A0 and Bob measures B1, then the results will still agree. They'll either get both +1 or both -1. Still easy to remember. If Alice measures A1 and Bob measures B0, then the results still agree. They're either both going to be +1 or both going to be -1. And then finally, if Alice measures A1 and Bob measures B1, okay, with the fourth combination here, then their results will disagree. Either Alice gets +1 and Bob gets -1, or Alice gets -1 and Bob gets +1. So easy to remember. Their results always agree except when she's doing A1 and he's doing B1. And then they're always opposite. Now this isn't a quantum state, but it's related to quantum states and it's got some nice properties that are easy to see. You can also see that this would lead to an argument like EPRs. Alice would say, look, if I measure A1, I can predict Bob's B1, or I can predict his B0, and I'm not doing anything to his particle, so he must have a definite B1 value, he must have a definite B0 value. If the Einstein-Podolsky-Rosen argument is right, then we would get the definiteness hypothesis here. Okay? So, can we fit the correlations, these supercorrelations, into the definiteness hypothesis? Well, Alice has one of these particles. Bob has his partner, they've got one of these pairs, so let's ask a question. Suppose that Alice's particle has a definite A0 value of +1. If definiteness is true, it's got either the +1 or -1 value, so suppose it's +1. Well then, that means Bob's B0 value, or in the 0,0 case, it's got to be +1. But it also means that his B1 value has to be +1. Just go back to that earlier slide. It'd be a little easier to see. Unfortunately, I can't show them both at once. But then, since Bob has a +1 for his B1, sorry, that's not what I meant to say, because Bob has a +1 for his B0, then our third principle about the A1 B0 case says Alice has a +1 for A1. Now you get the kicker. A1 would equal B1. Rule 4 from the previous slide said that can't happen. We just figured out that in the case we were looking at, Bob would have to have +1 for B0. That means Alice would have to have +1 for A1. And now we've got a problem. because Rule 4 says you can't have agreement in the A1, B1 case. Now, I'm just going to say this, we're not going to struggle with it. But the other choice is, well, that didn't work out. If we say that Alice has a definite +1 for her A0, that didn't work. So what if Alice has a definite -1 for her A0? It's one or the other. Will that work? Well, the same kind of argument shows that it won't. The problem is this. In this imaginary case, when they're both measuring their 0 case, A0, B0, the results agree. When Alice is doing 0 and Bob is measuring 1, the results agree. When Alice is doing 1 and Bob is doing 0, the results agree. And that forces, just by the logic of the definiteness hypothesis, that in the A1, B1 case, the results would have to agree. But we're imagining these supercorrelations where they don't agree. You sort of think, well, why are you imagining that? That seems like a crazy thing to imagine. Well, the reason we're imagining that is because quantum mechanics isn't quite this weird, but quantum mechanics is almost this weird. And that's where all of the fun starts. What we just saw is that if any pair fits our rules 1 through 3, it can't fit rule 4. And that means that if there really were supercorrelated pairs, the definiteness hypothesis that comes from EPR would have to be false. It would lead to a contradiction. It would be impossible. So, quantum theory doesn't predict supercorrelations, but it predicts something close. What we could show is that you get correlations in quantum mechanics that aren't 100% for a case like this, but they can be as high as about 80%. That 80% of the time, if they're both doing the A0, B0 case, they get the same result. 80% of the time, if it's A0, B1, they get the same result. And so on. And then a little bit of arithmetic that I'm not going to go through shows you that the probabilities would end up adding up to more than 100%. So we would get a contradiction once again, even though we have to do it together. So what's the point so far? What I've said here is that the EPR argument seems really reasonable. It says, what I do here doesn't affect what goes on over there. And then it uses a common sense principle to come up with this definiteness hypothesis. The position and the momentum are both definite over there. The spin is definite in direction d, and it's also definite in direction d prime. That's what the EPR reasoning leads to. And what Bell recognized is that that actually leads to empirical predictions. You can ask what quantum mechanics predicts for these statistics, and what quantum mechanics predicts will not fit the definiteness hypothesis. The definiteness hypothesis is empirically wrong. Okay? That's the point. Now, here's a little interim summary then, just to say what I said again. EPR noticed these funny correlations, and they give an argument that leads to the definiteness hypothesis. It would make sense of these correlations. The definiteness hypothesis is inconsistent with the supercorrelations we talked about. Quantum mechanics doesn't give those. And by a little extra argument that I didn't go through, it's also inconsistent with close to supercorrelations, and quantum mechanics does predict those. So, quantum mechanics doesn't fit with the definiteness hypothesis. But now we've got a puzzle. Yes, sir?
Is it a reasonable reformulation to say that the definiteness is the assumption that the measurement on one thing does not affect the measurement on the
yes.
other? In other words,
that's right.
only the combination of the two measurements at once is a single entity. Is that right?
That's a way of putting it that many people would be happy with. Certainly the idea that the measurement here doesn't affect things over there is definitely right. So, the moral is that if quantum mechanics is right, then either the definiteness hypothesis is wrong, that's one possibility, or in any case, another possibility that some people would throw in the mix here is this, is, well, maybe there really are signals going faster than light here. Maybe that's the explanation for these correlations. And that's a hypothesis that you shouldn't just dismiss. There are theories around that actually take that seriously. But in either case, Einstein was wrong, because Einstein rejected the action of the distance view, and he gave an argument that led to the definiteness hypothesis. So either way, Einstein's view is wrong. This is not to disrespect Einstein. This is just to say that even someone as brilliant as Einstein might be puzzled by some of the subtleties of quantum theory. It was a long time before people figured out how to get at what was going on with this argument. There's a slick way to see this that's kind of fun, and I'll just describe it briefly. EPR talked about pairs of systems. You can do a slick little thing with 3 systems, and you don't need to have any probabilities. It's named after 3 physicists, Girardi, Horn, and Zeilinger, and it's called the GHZ state, but that's just background. Here's what happens. We've got Alice, Bob, and Carol. Carol is usually the 3rd person in these scenarios. You need an extra one. So we've got these electrons. We can measure their spins, and we're going to consider 2 perpendicular directions, x and y. So Alice could measure x and measure y. Bob could measure spin x or spin y. Likewise, Carol. And the state predicts some 3-way correlations. Here's how it works. Suppose that one of them, doesn't matter which, is measuring x spin. Maybe it's Alice. And the other 2, say Bob and Carol, are measuring y spin. Suppose that's what's happening. For this special quantum state, here's what quantum mechanics says. The product of the 3 results will always be +1. So they might all get +1. Alice might get +1 and the other 2 might get -1, or the other cases. But quantum theory says the product will always be +1.
But that has to be true anyway. I mean,
no, it doesn't have to be true. But can we hold that question? It doesn't actually have to be true, because one possibility could be that one of them could get a minus and the other 2 could get plus. Okay? In other words, we're going to get 1 spin-up result, exactly 1 spin-up result, or exactly 3 spin-up results, as opposed to 2 spin-up results or no spin-up results. Okay? That's what's going to happen. That's what quantum mechanics predicts. And, you know, a silly little animation. Here would be a case where the green means they're all up. Here would be another case where we've got 1 green and 2 reds. That's the kind of thing that's going to happen. And it's either 3 greens or a green and 2 reds. That's what quantum mechanics predicts when you've got x spin here, y spin there, and y spin there, all being measured at once. So, first question is, that would lead to another fancier EPR argument. It's a little bit harder to state, but not much. You can probably imagine it yourself. We'd get the definiteness hypothesis once again. We'd get once again the hypothesis, Alice has a definite x and y spin, so does Bob, so does Carol. First question. We're talking about cases where one of them is measuring x spin, the other 2 are measuring y. In that case, is the definiteness hypothesis consistent? Does it actually work out so that you can describe it without a contradiction? And the answer is yes. Okay? I'm not going to worry about this, but I'll just skip through this because I think that we don't want to get into too many details, but just a little picture here to suggest that there's lots of ways it could happen. And here's a diagram here that gives in picture form all the ways it can happen. We can come back to this later if anyone's interested, but suffice it to say, there's no problem. All we were worried about was if one person does x spin, the other 2 do y spin, definiteness will work just fine, no problem. But on the one hand, the definiteness hypothesis works for all the cases where there's 1 x measurement and 2 y's, but there's something else that follows from the definiteness hypothesis, and it's not too hard to see. If the definiteness hypothesis is right, then Alice's particle has a definite x spin, Bob's has a definite y spin, Carol's has a definite y spin, likewise Alice has a definite y spin, Bob a definite x spin, and so on. And when we take the product of those 3 spin numbers for each of those cases, it's always got to be +1. That's another way of putting what we said. Therefore, when we multiply all those things together, that's just what I've done here. I've just taken those 9 terms and mushed them together and multiplied them. Well, plus 1 cubed is plus 1. Now, since they're just numbers, we can write them in another order. I've shoved all the x's out to the front, and I've grouped the y's together. So I've got the x's at the front, y1 squared, y2 squared, y3 squared. Well, I'm just multiplying the same things in a different order. It's still plus 1 is the product. But, okay, there's nonetheless something that we notice. y1 times y1, well, if they're both plus 1, it's plus 1. If they're both minus 1, it's still plus 1. The y squared is going to disappear. No matter whether it's y1 or y2 or y3. That term is going to disappear. It's just plus 1. And so what are we left with? Well, the definiteness hypothesis predicts the product of these definite x spins has got to be plus 1. And the problem is, here's what quantum mechanics says. It says the product has to be minus 1. The definiteness hypothesis predicts by simple arithmetic, I know I had to go over it a bit quickly, but it's really simple arithmetic, that the product of these x spins would have to be plus 1, and quantum mechanics says the product, if you make the measurement, will be minus 1. This is true. This is what quantum mechanics says, and although we can't do exactly this precise experiment, we have every reason to believe that if we could, it would work. The only reason we can't do exactly this precise experiment is just matters of it being a little bit too fussy to get to work in the lab. It's just issues about sort of experimental error. But everything we know suggests that this is basically right. So, in short, the definiteness hypothesis would have to say the product of those two numbers is plus 1. Quantum mechanics says the product of those 3 numbers is minus 1. The definiteness hypothesis from EPR conflicts with quantum mechanics. Oh dear. Well, what's going on here is that these states, the singlet state that we started talking about earlier on, the GHZ state that we've been talking about here, are what are called entangled states. And we can have some discussion about what this means, but and here's just sort of for those of you who like equations, state right now, okay. But what are some characteristics of entanglement? Well, the first thing, whenever you have an entangled state, you're going to get some correlations. But you cannot understand those correlations as I'm merely ignorant of the detailed facts of this thing and I'm ignorant of the detailed facts of that. The arithmetic breaks down. That's what we've in effect said here. Second, this is another way of saying the same thing. The correlations are stronger than you could get with any non-interacting classical systems. It is quantum. It isn't classical. And there is a sense in which the whole here is more than the sum of the parts. It may grate on your nerves when some people throw on the word holism, and in many contexts I understand why it grates on your nerves. But there is in quantum mechanics a certain precise sense in which you have something that people are happy to call holism. That and 50 cents might get you a bad cup of coffee, but nonetheless it's true. Okay? So, here's a coordinate animation. You can think of these two particles as entangling. Okay, and this means that they're getting mixed up with one another in ways that classical physics doesn't quite have ways of making sense of. Now we come to the big question. Well, is there spooky action at a distance here? And I'll tell you up front what I think the answer is. I do not know. Okay? But there are still some useful things that we can say. In other words, there are many views about how all this might be explained, if it needs to be explained at all. It's a big controversy in the foundations of physics, and I would just be one person offering my opinion. My opinion is not special. But we can sort of put the question this way. Do the correlations amount to spooky action in this? Well, it's not clear, but here's something really important. And this is the crucial thing that I would like you to take away from this discussion. You cannot use quantum entanglement to send signals or messages. You can't do it. And it's built into quantum mechanics at a very basic level, that anything that behaves that way is not quantum mechanics. It isn't that you have to get to some exotic part of quantum mechanics to derive that result. It's in there at the bottom. Okay? So when Alice and Bob are experimenting on their distant systems, distant meaning she's in one lab, he's in another, and they might be quite far apart, it's built into quantum theory from the very bottom, from the very beginning, the very rules for how quantum states work, that the probabilities for Bob's outcomes, Bob is making his measurements, are not influenced at all, are not dependent upon what Alice decides to do with her device. She can measure X spin, she can measure Y spin, she can measure spin in any direction she likes, and if that's all she does, she just decides which of those measurements to make, Bob isn't going to be able to tell. Nothing in the behavior of his particles will give the slightest hint which measurement she decided to make. No manipulation that Alice has any control over will make the slightest difference to the local pattern of statistics that Bob gets. And that's built into quantum theory at the bottom level. Okay? Likewise, nothing Bob can see, nothing Alice sees tells her about Bob's settings, and vice versa. So, well, how many have seen this movie? You know, I have a confession to make. I have a crush on Marlene Matlin. But in spite of that, no. Okay? No. There are some real problems with the picture of the quantum universe that movies like this and other such sources suggest. And so that's what I want to say a little bit about. The point that I just made, that nothing Alice does in her lab that she can manipulate can make the slightest difference to the pattern of results that Bob gets, nor vice versa. This is why you can't use quantum entanglement to perform magic. Okay? There are really nifty things that quantum entanglement does, but give you control over stuff going on somewhere else is not one of them. Okay? Even if there are quantum faster-than-light connections, I mean, ones that underlie entanglement as opposed to some other kind that we haven't discovered anything about, quantum theory itself says, you can't use them to send messages. You can't use them to control things at a distance. You cannot use them to perform telepathic communication. Okay? The way that somebody once put it in honor of John Bell, who brought so many of these issues to light, there is no quantum Bell telephone. Okay? There is no quantum Bell telephone. And as I was saying to one of you before the talk, it's not a question of whether there are or aren't psychic phenomena. That's a separate question. Even if it turned out that there are, and I'm not suggesting that any such thing is going to happen, but even if it turned out that there are, quantum entanglement would not explain them. Okay? Quantum mechanics is not the kind of thing that can do that kind of work. Furthermore, there's some other things. One of the things that you'll sometimes find people talking about, as in movies like What the Bleep, into which poor Marlene Matlin got sort of pulled in as the haunted star of the movie, who was somehow cured by quantum entanglement. Well, quantum entanglement is actually a very fragile kind of thing. So suppose that A and B are two electrons and they're entangled. Well, then it's really hard to preserve that entanglement. You've got to keep them both isolated from the surrounding environment. As soon as A interacts with this environment with all these air particles and all these molecules and zillions of things in it, what happens is this very tight entanglement that they started out with that gave us these nifty EPR correlations, it just kind of dissipates, just sort of withers away, so that it becomes, for all practical purposes, zero. Okay, it just isn't there anymore. This goes along with a phenomenon called decoherence, for any of you who happen to have heard the word, but nonetheless, the point is, quantum entanglement is fragile. And once again, this comes from the bottom level of quantum theory. But as soon as you get systems that are in a noisy environment, and noisy just means lots of stuff like dust particles, objects, and so on, and you start interacting with them, the tight entanglement gets spread out, dissipated through that environment, and then these correlations just disappear. Furthermore, I mean, I remember once having a conversation with a gentleman, who was very interested in these quantum phenomena, and he kind of, I think, wanted the world to be a certain way. Maybe many of us do. And so we had this conversation, and we talked about quantum mechanics and many things. And he said, well, don't you feel that as a result of this intense conversation we've had, that our brains are now entangled? Well, the answer is no. And the answer is no, not because I didn't find this gentleman a perfectly agreeable person to talk to, or wouldn't invite him to a cocktail party or anything like that. That's not the point. The point is that his brain and my brain are in the middle of an environment that is incredibly thermodynamically noisy, and quantum mechanics would say, nope, the entanglement would just, any entanglement there could possibly have been would just dissipate essentially into nothing. So our brains, for all practical purposes, couldn't get entangled in that way. So where does this leave us? This is where we'll finish. Well, these entanglement phenomena are pretty central to quantum mechanics. Schrödinger said that they were the central to human theory. And entanglement is wonderfully weird. There are all kinds of neat things about entanglement. But not that weird. So, I know I've gone over a bunch of stuff here, and I think the best thing to do now is to stop, and we can talk about it. If you have questions or things you want to raise, we can do that. Sir?
Maybe this is a bad analogy, but could these particles be acting like rubber bands, so to speak, to explain entanglement, that's entangled in a particle, like say, when they sort of stretch out in waves, and when they hit measurements, they sort of revert to particles again? Sort of like
there are views like that. The view that you're suggesting is one that some people would describe in a different way. They'd say that one view would say there are particles like electrons and so forth. And then there's this mysterious thing, I don't want to put too much stress on the word mysterious here, this complicated thing called the wave function. And that's a very important idea in quantum mechanics. And some people would say, well, the wave function really is a kind of a real thing. It's kind of like a field in its own way, only much more complicated. And so there's this wave function that connects these two particles, but it's not like a classical electromagnetic field in a whole bunch of ways. And so what they would say is that, yeah, sometimes you've got this sort of spread out wave that sort of collapses. And that's one view that some people have about what's going on here. It's one view among others. So that could be, but whether it really is, hard to say.
just follow up, could you say that maybe the speeds are instantaneous within the wave function?
What this view in its usual form says is that there is a particular frame of reference in which the speed really is instantaneous, and that special frame of reference has a special role to play in nature, but for various reasons it's not accessible to us which frame of reference that is. And this is a serious and interesting view that has led to serious and interesting physics, but we're not at the point now where we can test it experimentally. Some people hope we will be, but the experiments will be really hard. Sir?
You talked about, if I didn't misunderstand, you talked about the prohibitions for remote communications.
Yes.
Could you just relate that to, there are some experiments going on in
Yes.
remote communications. Could you talk about some of those in light of that prohibition?
Okay, there are some very interesting phenomena here that I'll try to kind of allude to. There's sort of a trick to it. There's a whole branch of the foundations of quantum mechanics that's concerned with things like quantum cryptography and so on, where you can somehow use quantum means to make communication between two distant people more secure and so on. And so quantum information is a fascinating subject that has some role to play, but briefly what makes it tricky is this. Suppose you and I have this shared entangled particle, and we're going to use this in some sort of way to sort of enable us to facilitate certain kinds of communication. It still turns out that the only way that we can do the full trick is that I actually do have to call you up and give you a bit of information. In other words, what happens is I can get a little bit more information to you by combining a classical channel like a telephone with quantum entanglement than you would expect classically. But in order for it to work, we have to have the good old-fashioned classical communication. And so it's not a case of merely quantum means allowing me to communicate with you. In all of these quantum communication protocols, there is a classical element of me giving you the old-fashioned way some information.
Is this more than the key management problem?
The key management problem is related to it. Yeah,
it's more than, but it's more than, in other words, there's more involved than that. The dependency on the classical channel.
Well, I don't know whether it's more or less involved, but the bottom line is that it's always going to be necessary in these cases for you to get any useful information from me, that part of that information comes through a classical channel. And once we combine the classical and quantum, you still get some very interesting things going on that you wouldn't get classically. But in order to do it, you've got to have the classical piece.
Thank you.
Sir, yes.
But no extrapolation of theory is required to use quantum phenomena, at least theoretically, for simple cryptography, right? Because cryptography simply requires that you and I have a parallel process to perform, even if we don't know what it is exactly.
Right.
And the quantum mechanics doesn't forbid that, right? It doesn't.
No, it doesn't. It doesn't. No. And the hope is that because of some of the features of the quantum state, you'll be able to do things like decode encrypted messages more efficiently. That's one thing that quantum computation might allow us to do. It might have these factoring algorithms that would allow a speed up that the classical computer wouldn't. This is all a field that is very much emerging now, and we're still scrambling to figure out what's what. I say we, as though I actually have the details. I don't. And there's also questions about whether you can use quantum mechanics as a way of detecting eavesdropping along the communication channel. And there's all kinds of fascinating things about that sort of thing. But once again, just to reiterate the point I made to this gentleman, whenever it's a case of me getting stuff to you, there's always going to be some classical element involved, even if it's marching a particle over to you or something like that.
Right, but the sharing of keys isn't an information transfer, and so it doesn't necessarily fall into that.
That's right. And then in that case, as I said, the quantum thing might be efficient ways of decoding by factoring large prime numbers. Yeah, not factoring large prime numbers, prime factoring large numbers. Yes. Yes, sir.
I'll ask perhaps laughable question that Einstein would ask. You start off saying that there's an electron over here, an electron over here, and I picture one electron in New York and one in Miami. Mm-hmm. But then looking at your diagrams, you mean that they really have to start off together.
That's a very important, yes. The way, what happens here is that there might be, for example, a certain kind of atomic decay process. And what this decay process will produce is two particles that might go off very, very fast from one another, but they do have a common origin. That's right. And that common origin is what got them into this entangled state in the first place. So, yeah, it's not, you can't just have, and that's actually a very good point, a very good question. There's no way to just sort of arbitrarily pick a particle here and pick a particle here and wave a quantum magic wand and get them entangled. There's got to be something in their history that allows for the entanglement to be created. There are fancy things called entanglement swappings, where I can have two entangled particles that were entangled as part of their history, and then a third particle, and there are fancy operations that I can do that will swap what's entangled with what, but still common origins are part of the story. Absolutely. Good question, sir. Yes, sir.
Yeah, all right. I'm trying to get this straight here.
Unlike
the definiteness hypothesis, or was it classical quantum mechanics, there does in fact appear to be some, I don't know whether you would call it spooky action at a distance, but some action at a distance that we don't know.
I'll give you a different word for that in a minute. Well, maybe here is the situation in a nutshell. There are some, let's use the word correlations, some seemingly spooky correlations, puzzling correlations that when we try to build a kind of a classical model for them, we fail. Okay? Now the question is, how do we understand these correlations? How do we think about them? And on some theories, theories that are beyond our capacity to test now, there actually is some kind of uncontrollable faster-than-light interaction. We can't control it, but it's there. On other ways of looking at it, there's a lovely phrase that the physicist Abner Shimoni came up with, and it's this. He said, no, it's not action at a distance, it's passion at a distance. And the idea was that there is some kind of relationship between these two particles that is not anything that was contemplated by classical physics, but calling it action at a distance is not right. He would say we really need a new category of relationship. And that's another view that some people take, and people will have disagreements about which is the better view. But, yeah. Yes, sir?
Would it be accurate to say that the second view comprises the idea that the two particles, that they're not two completely separate systems? Even though in some ways they may appear to be, that there are some
that's actually
element
right.
that still
That's
has
actually right. Yeah, one way that I sometimes like to put it is if you go way back to the ancient Greek atomists, and you go back to the 17th century when modern science was emerging, the view that people had about what would be a really nifty way to build a universe, because it would be so intelligible, was you build a universe out of little bits of hard matter. And they've got shape, and they've got hardness, and they move around and bash into one another and get hooked together. And the thought was, boy, if you could build a universe out of stuff like that, it would be really clear. You've got these distinct, well-defined things, and they're atomic in that sense, not just in the sense of being uncuttable, but being these discrete, separable things. Well, quantum mechanics seems to ask us to give that picture up. When you have entanglement, it seems that in some sense or another, and there's a lot of discussion about how this should be spelled out, these two things aren't just two completely distinct things. This is why the word holism has made its way into serious discussion and not just into popular discussion. There's something funny here. The quantum is not the classical.
I think this is related. Tell me if it's related. Can you relate the concept of non-locality, both on a popular and on a quantum context? We encountered that. Help us really understand how those two interact, both the popular, the mystical, and the quantum.
Yeah, I think it's probably something like this, and I think that some people in the physics community are guilty of using language a bit carelessly here. The word non-locality seems inevitably to suggest to many people that what I do here actually affects things over there. That my manipulation of stuff in my part of the lab is actually causally influencing stuff over there. But that's exactly what the controversy is about. That's exactly what people in the foundations of physics don't entirely agree about, whether that's the best way to understand these phenomena. And so the more careful sense of the word non-local here would be one that says something more like this. There are correlations here that cannot be accounted for by classical models. Whether those correlations bespeak some kind of literal influence is a much more delicate matter that's much more controversial. So I think that's the difference. Popularly, one thinks of it as, I do something over there and it changes the electron over there. The careful physicist or the careful philosopher of physics would say, not so fast, that's not so clear. Yeah.
I don't know, you might want to describe this, the hidden variable theories, because you sort of alluded to that there's some other property inside these things when they split that you read when you do the experiment.
That's exactly right. Yeah, if you use the term hidden variable theory, the definiteness hypothesis would be a case of a hidden variable theory. It would say, Einstein, Podolsky, and Rosen are right, there's something missing from, quantum theory itself. The something missing we'll call hidden variables. And if we understood those things, we'd understand how the world works. One kind of hidden variable view says, look, it's just like the analogy I used a few minutes ago. I make a letter, I give you a copy, and I give this gentleman a copy. And it's no surprise that when he looks at his letter, he knows what yours says. Okay, that's the kind of view that EPR might have. There are other hidden variable views that say, yeah, there is more stuff there, but we still got action at a distance. So the so-called Bohmian mechanics view of quantum mechanics, named after the physicist David Bohm, is a very serious research program that has, a lot of interesting work going on in it. And it does say that at some level there's some kind of action at a distance going on. But it's outside our control. And the theory guarantees it will remain outside our control. So we still can't use it for telepathy, for signaling, for getting information without classical means. And then other people say, ditch hidden variables, they aren't necessary, there are other ways of looking at the theory. You have to give up the urge to think that all the correlations have to have a mechanical explanation. Yeah. Yes, sir?
Scientists, others are accused often of using jargon. Maybe the problem is sort of the opposite. If you weren't using a word like entanglement,
yes,
people wouldn't confuse it. I mean, I think part of the problem is that you're using words which have a very technical, specific meaning, and people are taking them as common English words.
Well, actually, what happened here historically with this word entanglement is kind of interesting. What happened was that when Einstein, Podolsky, and Wilson wrote their paper back around 1935, Schrödinger himself, who also had many worries about quantum mechanics, looked at this work and did some work of his own, and he is the one who introduced the word entanglement into the discussion. My German is failing me at the moment. I can't bring the German word to mind, but it's one that translates very naturally as entanglement, and he didn't define it in a technical way. What bothered Schrödinger was it seemed to him that quantum mechanics did involve precisely some kind of spooky action at a distance. It seemed that way to Schrödinger. It seemed to Schrödinger that by doing stuff here, I could, at least with some probability, steer the system over there into any state I liked. He called this remote steering. He has a couple of fascinating papers about this. And so the word entanglement entered the discussion not as a technical term, but as Schrödinger's expression of his bewilderment about this apparent feature of quantum mechanics. And Schrödinger said, I hope it isn't true. I mean, he said, my hypothesis is that as soon as two particles start to move apart, the entanglement will decay and disappear. And that turns out not to be true. But, yeah, I mean, the vocabulary can be confusing, but it was an expression of puzzlement about the theory itself. Sir?
So is it physically possible when the two particles go, you measure, let's say, the direction and spin of one of them, and then you change it, flip it from a minus one to a positive one, and then measure the other one? You do that?
Once you've made the first measurement, the entanglement is broken. Yeah, that's a little, quantum entanglement really is fragile. After the first measurement, they're no longer entangled. And that's also why entanglement dissipates, because in order to measure my particle, I have to interact with it. And that allows me to make some predictions about the second one, but that interaction now creates a very different kind of a state in which that original entanglement is no longer there for me to use. I can only use it once to make one prediction, and then it's gone. Sir?
So when you had the two particles, you made your first measurement. How long does it ever dissipate, or can you wait a long time to make the second measurement?
As long as you, good question. As long as you have kept these things, the other particle isolated from its environment, you found a way to kind of protect it from stray air molecules or whatever, then you can wait as long as you like.
In fact,
it doesn't decay with time.
There's some relatively recent experiments.
That's right. Yes.
Where they measured them strictly at molecularly very disparate times. Are you going to be talking about those?
I don't really have anything in detail to say, though I know that the physicist Gisin has done some quite interesting experiments where you've had entanglement preserved over very clearly macroscopic distances, like sort of a kilometer.
And also where the indefiniteness, if you will, of one particle seemed to persist in a way that would have would have required the other one to communicate with it back in time.
Yeah, you know,
I just love to hear that experiment presented.
Yeah, you know, actually, this is something I've been meaning to turn my mind to because I have read the reports about this in the popular press, and the semi-popular press. For example, sometimes in things like Science News and so on, what people say about these things does not bear scrutiny. And so, I have a suspicion that when one looks at that case carefully, there will be something weird and interesting there. I have no doubt about that. And I have no doubt that Gissin has done a really good experiment. But that the careful description of it isn't going to involve us having, backward causation. That's my strong hunch, because it virtually always turns out that way. Sir? Yeah.
I doubt we have any proponents of QM telepathy here, but I'm curious how solid is the theory and experimental state in terms of there's just no way telepathy could exist and
See, I want to separate the issues. Okay. Initial disclaimer. Do I believe in telepathy? No, I don't see that we have any particularly good evidence to think there is such a thing. Do I think telepathy is absolutely impossible? Hey, I don't get to make up the universe. The way the universe is isn't up to me. So for all I know, I mean, I don't think it's at all likely, maybe it is, but that's a separate question. That's the point I want to make. If, in my wildest imagination, it turns out that there really is such a thing as telepathy, the point is simply this, that quantum mechanics and quantum entanglement can't be the explanation, because the way that the quantum math works plugs that hole. There's no room in quantum mechanics for that kind of thing. Whether quantum mechanics turns out to be not the whole story and some other physical theory that allows this is true, like I said, I don't get to make up the universe, and if that happens, well, it happens, but it won't be a quantum story. That's my only point here. Quantum mechanics doesn't provide any basis for telepathy. Whether or not anything else does is a separate question.
Okay.
Yeah. Sir?
Can I follow up on an earlier question about it being a wave function? I just wondered about the possibility. So suppose you had the two particles speeding off the detectors, and suppose before they hit the detectors, you were to drop, let's say, a huge lead block down the path. If they were actually a physical wave function, wouldn't that stop any entanglement from occurring?
That's a good question. It would depend very sensitively on the physics, but the answer is not necessarily. Suppose that I've got, just think of it this way, suppose I've got my particle here and I've got my particle there, and we haven't gotten around to performing the experiment yet. But between the two laboratories, I erect a huge lead barrier, okay? Sort of running, as you might think, well, I'm just sticking this lead barrier between the two parts of this wave function. It wouldn't make a darn bit of difference. It wouldn't make any difference at all.
Have they done experiments like that where they just put a barrier before the detectors?
Well, let's put it this way. I don't know whether they have or not, but what I do know is this. If someone did an experiment and that made a difference, quantum mechanics would be wrong. Now, quantum mechanics might be wrong, but my point is that the theory itself says that what you have here, once you've prepared particles in a certain way, is a kind of correlation that isn't going to be affected by things like putting barriers between them or waiting a while. And so that's why, that's one of the many reasons why conventional attempts to explain this don't work very well. So just to repeat, if that made a difference, quantum theory is wrong.
But so far as you know, no such experiment has been done.
I'm willing to bet that there have been experiments that have been done that if you analyze them in the right way, they amount to something like that. I'm willing to bet that. Even though that might not have been the point of the experiment, that if you looked at what was going on, you'd see, well, yeah, there's all kinds of junk going on between these two things. It would have, in effect, had the same kind of barrier effect, if a barrier effect were relevant. Barrier effects aren't relevant. That's the way they are.
They've done these action at a distance tests over, like, commercial phone line. Special phone lines, but the answer is the phone lines aren't a straight line, place to place. They've had to turn around and go around corners because, there are buildings in the way. They might have to go under a river. So in a sense, they put stuff in the middle.
Yep.
Because
Yeah, in any routine experiment, there's going to be all kinds of stuff in the middle, but if it made a difference, it would have already made a difference. It's fascinating. I mean, it's a very different kind of connection than what we're used to thinking of classically, and that's why it's such a great subject to think about.
His idea of the phone line, that just means that the path is curved.
No, right. I understand, but all I'm saying is this, is that if quantum mechanics is right, barriers are irrelevant. It would only be relevant if the particle actually interacted with the barrier. And then you've got good old-fashioned ending of entanglement because you've got a new interaction. But if the barrier is just between the two, not interacting with either of them, quantum mechanics says it doesn't matter. Sir?
Have you talked about the curious results of two polarizing filters and putting a third one in the middle?
That's
It's not entanglement, but
no, it's not entanglement. That is an effect that if you just had the three polarizers. I mean, I just have to say something quick because we don't have time to describe it for everybody. That's a case where if it was entirely local, you could explain it classically by saying that each time you put the polarizer in there, it disturbs the particle in a certain way.
Can I say it? I mean, what we're talking, this is an experiment anyone here can
Anyone
do.
can do with
if you get 3 pairs of polarized glasses.
Yeah.
And this is the experiment, and if you can explain it, then you're ready for the next Nobel Prize. Here's the issue. Take 2 pairs of polarized glasses and turn them. You know, the explanation you're being told is one is sort of let the light go only one direction, the other will let it go the other direction. Put them so they're 90 degrees apart so you see no light through them. Then you do something that if you can classically explain, more power to you. Take a third pair of polarized glasses. You would think if you put an additional pair of sunglasses in the middle, you'll have even less than 0 light coming out. I mean, it'll still be 0. Strangely enough, if you put the one in the middle so it's not at this angle or that one, put it at 45 or some other angle, you'll be able to see through all 3.
But classical electromagnetics
classically,
explain that.
yes.
Classical electromagnetics explain that. No, classical electromagnetics would explain that. I mean, this would be an interesting conversation. But nonetheless, it is a good example because by working your way out from that example, you do find nice ways of explaining some quantum roots. So it is a good example. And when you talk about it with photons, you don't just have the good old-fashioned classical explanation. But classically, this phenomenon was understood. Anyway, folks, my voice is giving out, but you've asked lots of really good questions. I really enjoyed talking with you. And thanks for being a great audience.